I'm going to begin with a letter from Kronecker to Mittag-Leffler. And thinking about it just before the talk, I'm not sure why I decided to bring in this kind of personal note, but it gives it a nice personal note. At the beginning, he's referring, when he says, I promised Hermite I would not bring up again the circumstance that made me so angry last year. He's referring to a tremendous incident that I won't go into in any detail, but the important part here is that Mittag-Leffler was a young organizer and promoter, and he had promoted a prize problem involving, well, I say, I'm not going into it. The point is that Kronecker had been very angry at Mittag-Leffler, and that tells us something about what he's referring to in this letter. And he's kind of saying, all right, we're going to forget about what happened last year and go on with it. And so now he's talking about his work in the letter, and he says that he's been tremendously busy. I've newly worked out a great deal of material for my lecture courses, and beyond that, and here we come to the point of the subject of my talk, I have put the foundations of algebra in an entirely new form. And this is a very big event, clearly, for him. He's very happy with it. He says, you will recall that I originally intended to give you my works on this subject for publication. So this refers to an earlier correspondence that he had with Mittag-Leffler when he talked about his objections to the works that were becoming current, specifically, I believe, of Cantor, and Kronecker's feelings about how mathematics should be done in an entirely different way than the way it was going. And he was going to submit to Mittag-Leffler for the Acta Mathematica his views on these matters. So we know then that he's talking not just about the foundations of algebra, but really the foundations of mathematics, which is what he was originally promising to send to Mittag-Leffler for publication. So the so-called fundamental theorem of algebra is replaced by my new fundamental theorem of general arithmetic. So that ties his views on the foundations of mathematics to this paper that he published a year after this letter was written with that title, A Fundamental Theorem of General Arithmetic. And then he goes on to say, I owe this beautiful and sure formulation of algebra to my sharp critique of the method of defining quantities, Gaussian Definitionen, I'll refer to that in a minute, that began with Heine. For some reason, in Kronecker's mind, he repeatedly refers to this as having started with Heine. We always think of it as starting with Cantor or with Dedekind or even Weierstrass. But in Kronecker's recollection and interpretation of events, and he was there and knew the people involved, Heine was the first. And to the precious Galois principle. It will appear in the 100th volume of our journal. Our journal is not going to the Acta Mathematica. Our journal is Krella's journal, of which Kronecker is the editor. So I'm going to use two projectors here to give you the chance to catch up on that if you wish. So this, as I said, this letter points to the paper as his definitive statement of his, and I emphasize positive criticism of the Gaussian Definitionen that were becoming current at that time and that he associated with Heine. This, it seems to me, is positive criticism in really quite a impressive way. He's always characterized, primarily, I guess, by E.T. Bell, but others. He's characterized as a very harsh critic who Hilbert called him a Verbotsdiktator. He just, all he did was say no. But on the contrary, you find in his writings very little about how this is the wrong way to do it. He spends all of his time in showing this is the right way to do it. Very positive criticism, I think. So this paper should be seen. I, for one, and many others have complained in the past that there's so little to be found of Kronecker's criticism of the transfinite methods that were becoming accepted at the time. And I never thought in the early part of my work that this paper was such a statement about the foundations of mathematics, because there's nothing negative in it. It's just, here is a fundamental theorem of arithmetic, and here's how to use it. Although Kronecker's views in this matter had scant influence in the development of algebra in the following decades, and perhaps I'm being a little negative there. I think Olaf gave us some reason to think that Kronecker's attitudes and work did have more influence than the storybook history of it all coming from Dedekind and Hilbert would have us believe. In any case, I'm making a small argument here that this theorem is certainly worth our attention, both because they bring a successful conclusion, to my way of thinking, to well over a century of thought about the fundamental theorem of algebra, and because they're central to Kronecker's approach to algebra, an approach that, valuable as it is in danger of remaining forever, but I hope less so as time goes by, remaining forever, in André Wei's words, buried in the impressive but seldom opened volumes of his complete works. I hope that people are opening them a little less seldom than was the case when Wei said that 50 years ago. So in the letter, he also says that the modern method, and the quotation marks are his, of defining quantities cannot be used. And this is a passage in the letter that I really only focused on, I think, after I began preparing this talk. It cannot be used for the definition of coefficients of two polynomials if one intends to use the algorithm for finding their greatest common divisor. Now, what this is a reference to, for those of you who are familiar with it, the kind of the L.E.J. Brouwer, Eric Bishop view of the foundations of mathematics. And there are certain operations that, well, I'm thinking in terms of the what Bishop called the principle of unlimited omniscience, or the principle of omniscience, that if you have an infinite sequence, you can regard it somehow as a completed thing, and you know whether if it's a sequence of zeros and ones, it is meaningful to say that it is either all zeros or there's a one. That's the principle of omniscience. And what Kronecker is saying here, in my interpretation, well, let me finish the quote, and then I'll say it a little bit more. If he does not elaborate, but he surely means that if, for example, you want to invert a non-zero element in the field Q with a cube root of 2 adjoined. Now, to do that, what you need to do, what you're doing is inverting a non-zero element of that field. A non-zero element of that field is represented by a polynomial of degree less than 3 in X, where X is a cube root of 3. To find the reciprocal of that element, what you need to do is to use the Euclidean algorithm to find the greatest common divisor of X squared minus 2 and the X cubed minus 2, and the greatest common divisor of X cubed minus 2 and that polynomial of degree less than 3 in X. You write their greatest common divisor as a sum of multiples of those two polynomials. Their greatest common divisor is 1 because the polynomial is irreducible, and the polynomial of degree less than 3 is therefore not a factor of it, has no common divisor. The greatest common divisor is 1, and in that way you get a reciprocal if it's AF I promised not to use the blackboard, and here I am, but here f is equal to x cubed minus 2, and g is equal to some polynomial of degree less than 3 that is to be inverted. So this, since you're working now mod x3 minus 2, this tells you that that 0 plus b times g is equal to 1. And therefore, b is your inverse of g. So if you want to invert a non-zero element of the field, it won't do to know the coefficients of f as real numbers. They must be known exactly as rational numbers, because the Euclidean algorithm otherwise won't work. You can't do a division if you have just a very, very good approximation to the thing that you're performing the Euclidean algorithm on. If there's any uncertainty about the coefficients here, that does not depend continuously on the coefficients. In particular, whether or not there is an inverse. You see, suppose, yes, to make it very concrete, if you don't know whether a is 1 or not, if you don't know whether it's 0 or not, you can't do this. And for a real number, you won't know whether it's 0 or not. You will only know that it's very, very nearly 0 or not very, very nearly 0. So that's what he's referring to, I think, and I never noticed that before I read this letter fairly carefully. So, in other words, in arithmetic and algebra, which were Kronecker's greatest interests, real numbers are not only inappropriate, but unacceptable. You cannot do the operations of mathematics. You can't do the ones in arithmetic and algebra if you only have approximations. And that's real numbers, and all the more so complex numbers. As you all know, Gauss's doctoral dissertation of 1799 was devoted to what we call the fundamental theorem of algebra and what Kronecker called the so-called fundamental theorem of algebra. Gauss called it neither of those things, I don't think. And Gauss criticized earlier proofs of Euler, Lagrange, and Laplace, saying they were circular insofar as they used computations with the roots of the polynomials in the course of proving that the roots were complex numbers. You see, that's the statement of the theorem that I'm focusing on, that a polynomial of degree n has n roots. But that's the simple form of the theorem. A polynomial of degree n has n roots. That goes back at least as far as Girard in the 17th century. But the theorem that Gauss was proving was the theorem that states that the roots are complex numbers. Or the way that he said it was that a polynomial of degree n can be factored into factors of degree 1 or 2 with real coefficients. Now, I'm not clear, it's partly a failure of my Latin, but I'm not clear what Gauss was assuming were the coefficients of that polynomial. My working assumption is that he intended integer coefficients. And I don't know, I won't go into that. For purposes of this talk, that is the fundamental theorem of algebra. Namely, a polynomial of degree n with integer coefficients has n complex roots. But to get back to a more philosophical plane, and how could one compute, what would justify computing with the roots of the polynomial before you had proved that they were complex numbers? Now, this is, in fact, the key question that Kronecker's Fundamentalstz answers. And to put it more tersely, how can you compute with the roots of a given polynomial, the roots of a given polynomial. And in a way, in the earlier versions of this talk, I emphasized how this was that Gauss himself later on came to realize that his criticisms of the earlier arguments maybe were not quite as damning as he thought, because his later proofs more or less, I'm thinking in particular of the second proof that he published quite some time later, followed something of the course of Euler, Lagrange, and Laplace, in that it consisted of two parts. The first part was a method of justifying computations with the roots. Once you know that you can compute with the roots, then you can use these techniques that earlier writers had used in order to prove that the roots can be realized as complex numbers. It breaks the theorem into those two steps. First, the ability to compute with the roots, and second, use of such computations to prove that the roots are complex numbers. Now, what are they if they aren't complex numbers? That's what's being answered by Kronecker's theorem, and that's what I want to focus on. In short, how can you compute with the roots of a given polynomial? And I'm thinking of a polynomial with integer coefficients. In a peculiar way, Galois gave the pragmatic answer to this question, how to compute with the roots of a polynomial. His answer was, on the one hand, unfounded, in a sense I will explain, at the same time it was paradoxically the foundation of Galois theory. It's really what Galois theory is all about. The essential idea was what Kronecker was referring to when he wrote of the precious Galois principle. I think there should be an umlaut there, yes? Der kirchliche Galoische Prinzip. It is, and this is Galois' method of procedure. Make use of the fact that you can evaluate symmetric polynomials. It's the theory of symmetric polynomials is at the heart of things here. You can evaluate symmetric polynomials of the roots to find a quantity with the two properties that, one, each root of a given polynomial, the given polynomial, can be expressed rationally in terms of this new quantity, and two, this new quantity is a root of a known polynomial. What this does, in modern terms, is to find a primitive element for the splitting field of a given polynomial. If that's not familiar, I think I'll give you a complete example so that you'll see exactly how that works. So I'll stick with this polynomial x cubed minus 2. It has three roots, according to this principle, and that's what Galois overlooked, or didn't overlook. I don't know how he felt about it, but he doesn't mention it. Without going into what these three roots might be, we do know what the symmetric polynomials in them are. Their sum is 0 because the coefficient of x squared in the polynomial is 0. Their products 2 at a time is 0 because the linear term is 0. And their product is 2 because the constant term is minus 2 in the polynomial. So that's the basic gimmick, that you don't know what the roots are, you don't know how to compute with the roots, but you do know the symmetric polynomials in the roots. You know the elementary symmetric polynomials, and therefore you know all symmetric polynomials. You can evaluate them quite simply. Now, let's let T, and T is going to be this quantity that is the Galois resolvent, and that describes how to compute with A, B, and C. We don't know what A, B, and C are, but we can discover how to compute with them by using the tasty or the precious Galois principle. So if I can compute with them, then I can certainly talk about the difference of two of them. So a minus b is the difference of two of those roots. T is the root of a polynomial of degree 6. Namely, the polynomial whose roots are a minus b and b minus a and c minus b and b minus c and so forth. There are 6 possibilities for a difference of two of the roots. You take the product of those 6 linear polynomials, and you get a polynomial in X of degree 6 whose coefficients are symmetric in A, B, and C and can therefore be evaluated. Here, of course, we're computing with A, B, and C as if we knew how, and of course we do know how to compute with symmetric functions of them, even if we don't know what they are. Galois seems never to have bothered himself with the question of what they were. I mean, it may be that, well, I don't know, and I won't try to read his mind what his attitudes toward these computations were, but he did them. That polynomial of degree 6 is, in fact, x cubed minus 108, x to the 6th plus 108. In other words, if you multiply this out and evaluate it, and I can show you that fairly quickly. I won't linger on it, but if you combine the terms in pairs, you have a difference times a sum. So you can combine those, and so you get a product of 3 factors, each of degree 2 and x. So all we have to do is to evaluate the coefficients of x to the 4th, because the leading coefficient is obviously 1. The coefficients of x to the 4th, x squared, and the constant term. The first one is minus the sum of the squares of the differences. And this is just a little algebraic simplification. When you square them out, you get a square plus twice the cross term. So that's this, and we know that the sum of the products 2 at a time is 0. So that really, well, I guess I don't get rid of that first. I first observe that the square of a plus b plus c is equal to a squared plus b squared plus c squared, plus some terms that are combined into that. And now it's minus 2 times 0 squared plus 6 times 0 is 0. So that shows you that the coefficient of x to the 4th is 0. And the coefficient of x squared is also 0 by a similar argument. The constant term, I'm saying here, is plus 108, and that's a simple trick that I think probably everybody knew at the time that Galois was writing, and at the time that all of these mathematicians were working, it was there is a certain facility with symmetric polynomials that I'm sure that every mathematician learned how to compute with symmetric polynomials. This certainly is very strong in 18th century mathematics, and already Isaac Newton in the 17th century was computing with symmetric polynomials with great mastery. But this is what the top formula there is, what is known as a Vandermonde determinant. That's a simple expansion that you can do, and it works for n roots as well, the analogous formula. Both sides are polynomials of degree 3. They both contain b times c squared, and both are 0 when any two of the variables are equal, and therefore the two sides are equal. And therefore, the thing that we're looking at, which is the square of the product of those 3 possible differences, is the determinant of this product of that matrix with its transpose. And that turns out to be something that's very easy to evaluate. When you do the multiplication, you just get sums of powers of the 3 roots. And there's something called Newton's theorem that everybody used to know, maybe everybody still does, that tells you how to evaluate a sum of nth powers of the roots of a polynomial using the elementary symmetric polynomials. In this case, it's especially easy because we know that these 2 terms are both 0. We just saw that the sum of the squares is 0 in the last slide. And the sum of the cubes the cube of a root is 2. So the sum of the cubes is just 6, and the sum of the fourth powers is twice the sum of the first powers. And therefore, that's 0. And therefore, what we're looking at is the determinant of this matrix. Go away. Can you all see that? Fine. I think it's on the mirror or the lens. Anyway, this determinant then is minus 108, and therefore the polynomial is, as I said. So that's. I wanted to say a few words about the computation with symmetric polynomials and the trickery that can be involved, and how I believe that mathematicians of that period were very comfortable with it and learned in it. Thus, the difference t equals a minus b of any two roots of x cubed minus 2 is a root of this 6th degree polynomial. But that's, of course, the easy part of the Galois program. The hard part is to express the roots rationally in terms of t. I'll spend a moment on this because Peter Neumann called my reconstruction of Galois' proof far-fetched. In my book on Galois theory, I describe how I believe Galois meant to prove his lemma 3, and Peter thought that it was far-fetched, and I don't think that it is. I feel that I have some new evidence for it in the form of a following sentence of Abel published a few years before Galois' work, and which I only recently came across. But Abel says, when a quantity satisfies at the same time two given algebraic equations, these equations have a common factor of the first degree. Well, that's very commonplace. Everybody knows that. And Olaf just referred to that. When one supposes that they have no other common factor than this one can always, and here's the part that I added emphasis, as one knows. Everybody at the time, I think, would know that. You can express the unknown as a rational function of the coefficients of the two equations. So, in any case, Abel felt that that was a pretty well-known fact about the theory of the equations. So I'm going to show you how to use that. First, I'll observe that this formula holds. V is just a new unknown here. And I'm still computing with my same roots A, B, and C of cube roots of 2. So v minus b times v minus c is I'll just multiply numerator and denominator by v minus a. But now the numerator is v cubed minus 2. By definition, the denominator is v minus a. But that's the same as v cubed minus a cubed over v minus a. And now I can do the division algebraically, and I get v squared plus av plus a squared. And exactly the same trick works for an arbitrary polynomial. If I take the product of all the factors except v minus a and multiply numerator and denominator by v minus a, I get f of v in the numerator, but that's the same as f of v minus f of a because f of a is 0. A is a root. So this is f of v minus f of a over v minus a, and this is a polynomial that's divisible by v minus a algebraically. So you can carry out the division, and you will get a polynomial in v and a. So what does this do? It expresses the elementary symmetric polynomials in the roots other than a as rational functions in a. In our particular example, the sum of b and c is minus a, and as we knew, because a plus b plus c is 0. So the sum of b and c is minus a, and the product of b and c is a squared, because abc is equal to 2, and a cubed is equal to 2. So if I divide both sides by a, I get that b times c is equal to a squared. And in the same way, you can find the elementary symmetric polynomials in all the roots but one, always as a rational function of the one remaining root. And in the particular case that we're dealing with, if I just set v equal to minus t plus a, then this is v minus b times v minus c, and that's the same as v squared plus a times v plus a squared. Squaring things out, and multiplying things out, I get these terms, and combining terms, I get t squared minus 3at plus 3a squared. So there is an equation that is satisfied by t and a. Namely, it's 0 because, of course, by definition, the first factor is 0. I think that's on the next slide. Yes. But the first factor on the left is 0 by definition of t, so we have the two relations satisfied by a. First, a cubed minus 2 is 0, and secondly, t squared minus 3at plus 3a squared is 0. So these are two equations satisfied by a. By a, yes. Their coefficients are rational in t. In the first case, they don't involve t at all. In the second case, the coefficients are polynomials in t. Therefore, by the principle that Abel states, we have two now, why is a the only solution of both equations? Because the first equation is irreducible,